So this is lesson 3, and we are going to focus on calculating the mass and average atomic weight of an atom. They're two completely different things, so we need to look at that. First, I would like to show you a little music video from Mark Rosengarten on the history of the atom. It's called Atomos Atomos, and we'll watch that together.
Long ago, two Greeks were consuming grapes and wine. They had a great idea that was really, really fine. If you took a substance and divided it enough, eventually you get the smallest particle of stuff. 1800, Dalton said the atom is a sphere. It cannot be divided any smaller, do not fear. He did a lot of work with pressure made by gas, and said that atoms of each element had different mass. Atomos, atomos, everything's made of you. You permeate the universe and everything we do. You are really small, and although we cannot see, through many years of science we know that you must be. In 1897, J.J. Thomson cathode rays, he noticed they deflected when a charge was in their way. They must be made of particles that have a minus charge. He called these things electrons and said that they're not large. Said the atom was a sphere, both positive and diffuse, with negative electrons which then could be pried loose. The atom's not indivisible, it's made of smaller stuff, but not even this amazing fact would prove to be enough. In 1911, Ernest Rutherford did prove, through a piece of gold foil alpha particles could move. Some of them deflected, but most just went right through. So what was his deduction from the way these alphas flew? The atom's mostly empty space with a nucleus within, and around this empty space electrons did their spin. This is very close to the model used today, but then Niels Bohr came in with something else to say. Atomos, atomos, everything's made of you. You permeate the universe and everything we do. You are really small, and although we cannot see, through many years of science we know that you must be. Bohr said that electrons have certain energies that are divided into levels like a ladder, if you please. If electrons are excited, they will move up high, and when they fall back down, photons of light will fly. Many other scientists have built on this idea, and now quantum mechanics has started its career. Electrons have sublevels and orbitals as well that are a lot more intricate than Bohr's electron shells. Atoms, atoms, we know that you exist. Through centuries of science, the concept still persists. You are really small, and although we cannot see, the model keeps developing toward reality. You are really small, and although we cannot see, the model keeps developing towards reality. Oh yeah.
So I hope you like that little video. It's cute, and I like to incorporate these into the lessons as we go. So let's start with calculating atomic mass for any element. So atomic mass is completely different than mass number. Mass number, remember, is the total number of protons plus neutrons. Completely different. Remember, protons have a mass of 1 AMU, and neutrons have a mass of 1 AMU. So each proton and each neutron contribute to the total mass to equal the mass number. Electrons are negligible, and it's 1 over 1836 of an AMU. So therefore their mass doesn't really contribute to the total mass number. So when we calculate atomic mass, we have to do this weighted average versus a straight average. So it's not add up all of their masses and divide by 3 or whatever it is. We have to look at the naturally occurring isotopes. So if we remember, let's recall, isotopes are atoms of the same element but have different number of neutrons. And if we have different number of neutrons, then that's going to change our mass number. And therefore, it's also going to affect the overall atomic mass. So we need to figure that out based on weighted average. So the weighted average is the addition of the abundance of each isotope times the mass of each isotope. And we add those all up to get the atomic mass, or weighted atomic mass. So let's look at some examples here. All right, so we have C12 and C13. So they are both isotopes. C12 is 98.89% in abundance in nature. So 98.89% of all carbon isotopes are C12. And 1.11% of carbon isotopes are C13. So what we have to do is, the first step is multiply the mass of each separate isotope by its percent abundance in decimal form. So this is really, really important, because if we change it, if we leave it in percentages, we're going to end up with a completely different number. So first, let's take the abundance. So we have 0.9889. So what I did was I converted this to decimal. So you're going to divide by 100. Okay, and same thing here. Divide by 100 to convert to a decimal. So we have 0.9889, and we're going to multiply this by the mass of the carbon. Okay, and how do we get that? We're going to look at that in a second. Okay, so for C12, we're going to put the mass as 12, and then we're going to get an answer for that one. And then for the second isotope, we're going to do 0.0111 times 13, because that would be the mass number. We don't have the actual mass of the isotope. All right, so let's go up here to our calculator, and we can do 0.9. Okay, so when I multiply 0.9889 times 12, my calculator shows 11.8668. 0.0111 times 13 equals 0.1443. Okay, so now we take these numbers and we're going to go to step 2. Step 2, we simply just add these up. And we go from there. All right, so let's put this back up here. We have isotope 1, which is C12, okay, and that is 11.8668 AMUs. And then C13 isotope, and this is the weighted average mass. Okay, isotope number 2 is 0.1443 AMU. All right, so let's add those up. So we have 11.8668 plus 0.1443, and we get 12.0111. Now for this, we don't necessarily have to use sig figs. If you notice on the periodic table for carbon, 12 atomic mass reads 12.0111 AMU. Okay, and that is where we get that decimal, weighted average mass. We can also call that WAM, if that helps. Weighted average mass. So let's do another example, and the more we do, the easier it will get. Okay, and I say that a lot. Practice makes perfect. So let's look at boron. It has 2 isotopes naturally occurring, and we have masses here, and we have percent abundance. So we're going to look at boron, and we could say that's boron 10. Okay, first we do the multiplication, so step 1. All right, we have boron 11 and boron 10. So step 1, we are going to take our mass, 0.130, and multiply that by the percent abundance in decimal form. So another way is just to move the decimal place 2 over to the left. So that's 0.199. And then for boron 11, we have 11.0093. Multiply that by 0.801. And then what we're going to do is we add these up after we're done. All right, so I'm going to do the multiplication. Okay, so when I add up their masses, or their weighted atomic masses, average masses, we get a total of 10.8110363 AMUs. Okay, so I simply just multiply the mass times the percentage in decimal, okay, for each isotope, add them up, and that's the WAM. That's what we'll see on the periodic table. All right, so let's look at example 3. So hydrogen has 3 isotopes. The names, very important, we do need to know these: protium, deuterium, and tritium. So pro can mean 1, okay, the prefix can mean 1, so notice how the mass is 1. Deuterium, so duo means 2, tri means 3, so this is how this is connected here. Prefix with the mass number, okay, tri, duo, 2, okay, and pro meaning 1. So percent abundance, look at that, protium, 99% of all hydrogen isotopes are hydrogen 1, only 0.6% are hydrogen 2, and only 0.4% are hydrogen 3. So in order to set this up, okay, first we're going to get the mass, and we don't have a decimal. We're just going to use this as our mass number. All right, so we have 1 for hydrogen 1 times 0.99, okay. First we're going to get that, and then we have to do 2 for hydrogen 2, or deuterium, times 0.06%, and then tritium 3, that's the mass, times 0.04. And we will multiply these out first, then we're going to add all of them, and that will be our weighted average mass for hydrogen. Okay guys, so I made a mistake on the percentages. We had to go back and move the decimal place over one more. So I did my division incorrectly, and once again I made a mistake. So I went back and fixed this here. So 0.006 is equal to 0.6%, and 0.004 is equal to 0.4%, and we need to multiply those by the mass numbers over here. So when we do that, I get these values over here: 0.199 AMUs for hydrogen 1, 0.012 AMU, atomic mass unit, for hydrogen 2, and 0.012 AMUs for hydrogen 3. I add those three up and I get 1.014. That is the weighted average mass for hydrogen. Okay, so ultimately, what is the difference between atomic mass versus mass number? Okay, this is the weighted average mass of all naturally occurring isotopes of an element. And the mass number is simply just the sum of all protons and neutrons in the nucleus of an atom of an element. Okay, and that would end our lesson 3. And please practice calculating WHAM in your homework packets. I want you to do this before you come to class. That way you can have a heads up and be prepared to ask any questions. We're going to be playing catch up this week, so again, make sure that you have at least pages 2 through, I would say, about 5 right now in packets complete, so we can go over those in class. Thank you, guys.